Welcome back, everybody. Now for part 2 of sampling distributions and the central limit theorem. Now we're going to be focused more on applications, showing you how this math is slightly different from the normal distribution and showing you some of the different ways it can be used. All right, but let's go over some of the properties of distribution of the sample mean. So some properties that we need to remember. The first one is the mean of the sample means will equal the population mean. And I'm not sure I have to say too much about this. We kind of proved it in part 1. All right, so number 2, all right, is the standard deviation of the sample means will be lower than the standard deviation of the population. And again, I think we said that in part 1, not really a surprise. The addition is, right, and it will equal standard deviation divided by the square root of our sample size of the population. So standard deviation of the population divided by sample square root of the sample size. Like I said, these two properties we explored in part 1. The third one is the one we're going to explore today, and that is, so number 3, of course I write the wrong letter, as the sample size increases, the shape of the distribution of the sample means taken with replacement from the population mean mu and standard deviation will approach the normal distribution and we'll have a mean of mu and the standard deviation times the square divided by the square root of our sample size. And this right here, my friends, is called the central limit theorem. The requirement for the central limit theorem is that n is greater than or equal to 30, or it's stated in the problem, I'll say whatever variable is normally distributed. So unless that's stated in the problem, or n is greater than or equal to 30, we can use that. We can use the central limit theorem. If the sample is not greater than 30, and it doesn't say that whatever variable we're using is normally distributed, the central limit theorem falls apart. All right, so now we're going to go through two problems. And I hope that these two problems are really going to highlight when we're going to use the central limit theorem and when we're just going to do our regular normal distribution kind of techniques. So let's take a look. Here's the first example. The average age of a vehicle registered in the United States is 8 years or 96 months. Assume the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that the mean of their ages is between 90 and 100 months. All right, so two things that I want to point out right in the problem is that we're talking about a random sample of 36 vehicles. So with our normal distribution, we're always saying, if we draw one randomly selected vehicle, randomly selected person, then we did our regular normal distribution stuff. This problem's slightly different. It's talking about if we draw a random sample of 36 vehicles. The other thing I want to point out is that our sample size is 36, which is greater than or equal to 30, which means that we can use our central limit theorem formulas. Now, the Z formula for the central limit theorem is going to be x bar minus mu over our standard deviation divided by the square root of our sample size. Right? Slightly different than the regular Z formula. The regular Z formula was just x minus mu over the standard deviation. All right? So we are most definitely using this one. So I'm going to highlight it because we have all the elements, right? The average age of a vehicle registered is 96 months. So X bar is 96 and our mu is 96. Our X bar, right, is going to be the mean of their ages is between 90 and 100 months. So X bar is 90 minus 96. And it's going to be over 16 is our standard deviation divided by the square root of 36, which is our sample size. So I want you to give this a pause right now, do the math on your calculator, and when you come back, I'll talk about the answer on the back end. All right, hopefully you did the math and got, as I did, negative 2.25 as our first z-score. Our second z is going to take our other average, 100 minus 96, and again, 16 divided by the square root of 36. So once again, I'm going to ask you to pause the video and see what our z-score is. Okay, hopefully you paused the video to see what the z-score is. I got a z-score of 1.50. All right, so let's start making your picture. So there's your average 96. Just estimate, put 100s on this side, 90s on this side, and we're looking for how much is between 90 and 100. All right, so I got negative 2.25 as one z and 1.50 as the other z. Why don't you go to the chart, get your areas, and we'll talk about the answer on the back end. All right. All right, so hopefully you looked up your areas on the chart. You're going to get your area for 1.50. You're going to subtract off your area for negative 2.25. I got an area of 0.921. So that is the probability of obtaining a sample mean between 90 and 100 months. All right, let's move on to the second problem. That is right here. The average number of pounds of meat a person consumes each year is 218.4 pounds. Assume the standard deviation of 25 pounds, and the distribution is approximately normal. Find the probability that a person selected at random consumes less than 224 pounds per year. All right, so I just want to take a minute to point out something, all right? So a lot of people ignore this kind of statement, but it's here. So it says, assume the distribution is approximately normal. That means that if we had a sample of less than 30, this statement would mean that we could use the central limit theorem. However, Part A is not asking about a sample, is it? Part A is saying, find the probability that a person selected at random. So if we're talking about a person selected at random, all right, that means we're going to use our regular z-score formula, which is z equals x minus mu over our standard deviation, which is 224 minus 218.4 over 25. Pause the video, let's do the math, and we'll talk about the answer on the back end. Okay, hopefully you paused the video to work out your z-score. My z-score was 0.22. All right, and because I want to know about eating less, that is area to the left. So I want to go to my z-chart, and I want to look up my area for 0.022. And I find, okay, sorry about that. So the probability, so the answer, the probability of selecting an individual who consumes less than 224 pounds of meat is 0.5871. All right, so let's take a look at part B. Now, part B says if a sample of 40 individuals is selected, Find the probability that the mean of the sample will be less than 224 pounds per year. So again, let's point out that we're not asking for a randomly selected individual. We're saying if a sample of 40 individuals. Sample of 40 individuals should indicate central limit theorem, and our n is greater than or equal to 30, so we can use it. Even if our n wasn't greater than or equal to 30, remember we had that statement earlier that said the distribution is approximately normal. All right, so we have to adjust our formula. So now z is, let's go back and see. So our x bar is going to be 224 minus our mean 218.4 all over the standard deviation divided by the square root of the sample size. So why don't you pause the video, take a minute, and get your z. All right, hopefully you got your z, and it's the same as mine. Mine was 1.42. Now you guys are experts at going to the z chart, so I'm going to ask you to pause the video once more, go to that z chart, and let's see what that area is to the left, because we're talking about less. So pause the video, do it now. Okay. Hopefully you paused the video, and I got that the probability is 0.9222 on my z chart. So in that second problem, part A, we had an individual, normal distribution. Part B, we had a sample of 40, central limit theorem. All right, so that really showed us in one problem how we could need both. So please, when you're reading the problem, read it carefully. The only clue will be those few words, a sample of 40 individuals or a randomly selected individual. That's the key to victory with the central limit theorem. Thanks, guys, for listening, and I'll see you next time.